Let's consider a function sine of x cubed. We'll call it h, and this function h is, by definition, a composition of two functions. If we're interested in talking about how h changes with respect to its independent variable x, then we would do the derivative, h prime. But notice that because this is a composite function, there's a bit of a chain reaction happening. When you plug in a value for x, you're changing x. That causes a change in x cubed, and then that would cause a change in the overall function h. So when we talk about how h changes with respect to x, we have to recognize that h is changing first with respect to x cubed, and x cubed is changing with respect to x. So we have to go through both changes to see the total change. We can generalize this for a composition of functions with two generic functions like f and g. If we wanted to see the overall change in our function, we would look at how f changes with respect to g, then how g changes with respect to x. This is the idea behind the chain rule. Let's derive the actual formula for the chain rule using an example like our h of x function. So we'll start by using the definition of a derivative at a point. So we have our limit definition applied to the function sine of x cubed. And we can't do direct substitution here. We would get an indeterminate form, but we do know that we can manipulate this limit to make it so that we're able to evaluate it. First thing I'm going to do is multiply by 1. But it's not 1 in the strictest sense. It's an expression that's equal to 1. X cubed minus a cubed divided by itself will be equal to 1. So we multiply our limit by that value, and then we're going to regroup our denominators. So really just have the denominators swap, which is okay because multiplication is commutative. So I just reversed the order of our multiplication in the denominators of our fractions. Next, we're going to apply our limit laws. Right now we have one limit symbol, but we're taking the limit of a product, and our limit laws say that the limit of a product is the product of the limits. So each of our factors will get its own limit symbol. Looking at the second limit, so the limit where x approaches a of x cubed minus a cubed divided by x minus a, that looks like the limit definition of the derivative for a function at the point a. And the function that it looks like it's using is x cubed. So that limit right there is by definition the derivative of the function x cubed evaluated at a. And we know that that derivative is equal to 3a squared. We could evaluate the limit to find that, or we could use our derivative rules. So we'll replace that second limit with its value, 3a squared. Next, we have to make a substitution. We're going to replace our x cubed terms with a simple letter, u. So we call this a u substitution. This is going to reduce the complexity of the expression that we're looking at, but it does require us to process a few other changes. If we pull out all of the x cubes and replace them with u, then we wouldn't want our limit to say x is approaching a anymore, because our expression will no longer have x in it, it'll have u in it. So what happens to u when we allow x to approach a? Well, u would start to approach a cubed. So we're going to replace all of our x cubes with u, and then we're going to replace our limit notation with u approaching a cubed. Now that we have our limit written this way, we can see that we are looking at the definition of the derivative for sine of u, and that is being evaluated at a cubed. We know the derivative of sine is cosine, and if we evaluate that derivative at a cubed, then we would have cosine of a cubed. So the derivative here for h would be cosine a cubed times 3a squared. Essentially, we broke our composition into two functions, the inside function and the outside function. We took the derivative of the outside and left the inside in there. And then we multiplied all of that by the derivative of the inside. And that's how we get our chain rule. So to find this derivative, we took the derivative of sine with respect to the dummy variable u, where we replaced u with a cubed, and then we multiplied that by the derivative of x cubed, where we plugged in a for x. We can generalize this chain rule to be applied to any composite function where we have, say, two functions, f and g. F would be the function on the outer part, and g would be what is plugged inside of the composition. So to find this derivative, we would take the derivative of the outside and then plug that inside function back in, multiply it to the derivative of our inside function. Using our prime notation, that would look like f prime with g of x plugged inside of that derivative, then multiply by g prime. Or we can use the fraction notation where we have df dg, so the derivative of the outside function f with respect to its perspective inside variable g, then multiply the derivative of the inside function dg dx. And this is our chain rule.